All right, let's get started. Today we have Dhawal Gupta, who's going to tell us about optimizations for TD.
Hi. So yeah, just go through these messages, and I'll start now. So this is something which I'm working on and trying to study somewhat of how optimization for TD might work in different cases. This is the work that I'm currently doing with Martha, Andy Patterson, and Shivam. So the question that I'm trying to investigate over here is, can adaptive step-size methods from the deep learning community actually be used for reinforcement learning? And if they can help us counter some of the divergence issues that we see in the TD learning case. So my structure of the talk is going to be like this, where I'm first going to introduce the mean squared projected Bayesian error. I'm going to discuss some divergence, the adaptive step size methods, and some empirical results.
Dhawal,
So yeah,
sorry, we just see your uh, keynote, like the main window, not the presentation window.
okay, wait. I think my laptop is acting up. Like, are you able to see the key only the keynote window?
Yeah.
Wait, I'm also not able to see my mouse. Is it okay now?
Yeah, much better. If you just want to then shift between the slides here, that would be
Oh, okay. You're
fine.
still not able to see the presentation. Okay.
No, it's okay. You can do this too. This works.
Yeah. Okay. So
We can see your nose, so okay, never mind.
yeah. So I'm going to use the mean squared projected Bayesian error just because the zero of the mean squared projected Bayesian error coincides with the TD solution, and the Monte Carlo solution normally gives us the minimum value error. And the expected form of the TD zero update looks something like this, where for the convergence of TD zero, we want this system to be having like to have all the eigenvalues less than one. For that, we normally require the A matrix to be positive semi-definite. And like the A matrix depends upon the feature representation, the behavior policy of a system, and the target policy of a system. Now, moving on to the divergence of temporal difference learning, we move to the deadly triad, where whenever we have function approximation, bootstrapping, and off-policy learning, TD learning often mostly diverges. And the core reason for the off-policy divergence is because of the policy mismatch between the behavior policy, which is mu, the stationary distribution, and the transition matrix of the target policy. So for convergence, we need this whole vector to have all positives. And when these two quantities mismatch, we can get a negative value. I'll show an example with the Baird's counterexample in the later part of the presentation. So how would an adaptive step size method from, let's say, Adam or RMS prop look like for TD0? I would just represent the adaptive step size method with the G matrix over here. And normally we add the G matrix in front of the A matrix. This can come from, and the G matrix can encode environmental and behavioral information. And in the supervised learning community, it mostly helps with the faster convergence and stability of the learning. G matrix can come from Adam RMS prop, or other methods like AMS grad and ADA-grad. Moving on to Baird's counterexample. So it's a very famous example which shows divergence of TD learning, where we have an environment with 7 states, and our feature representation is over-parameterized, meaning that we have 8 features for 7 states. The behavior policy is deterministic in the sense that all these 6 states, all these states transition to the 7th state, and our target policy is like that, and the behavior policy is uniform, wherein from each state we can transition to any other state with equal probability. And this value in the case of Bayes counterexample, has a negative term, which shows that it causes divergence, like it will diverge. This is like this last element in this is negative. And because of the over parameterization of the weight vector, we have a like infinite number of solutions, which is normally in the direction of this vector. So now I'm going to move on to some empirical results, which show how Adam and RMS prop behaves on these problems. And this is my like kind of a legend of how the results are going to be. The x-axis is normally going to show the steps or the number of updates. The y-axis is going to be a metric, like the mean square projected Bellman error, or the angle, or the length of a vector, and these are going to be the color codes. I keep mentioning the algorithms, so for ease of listening. Now, in the normal Bayes counterexample case, we see that the SGD diverges, like the normal update diverges, and the mean square projected Bellman error goes to infinity. But if we reduce the gamma to 0.11, which makes this vector to have a positive element over here, we actually see the thing to converge to 0 PVE. Yeah, and like in the case of divergence, we actually see that the angle goes to 90 degrees from the solution vector. Like this is the angle of the weight vector to the solution vector, and the norm also goes to infinity. So it's not like the vector is like trying to align to the right direction also. Now, when we apply RMS prop and Adam to this problem, we actually see the mean square projected Bellman error goes down. And so this is basically optimized for the end performance, where we optimize for the last 10% of the performance over all the parameters that we sweep. And when we optimize for the area under the curve, which is the second graph, we see that Adam solution kind of oscillates. And to study this further, when we run the system for a larger amount of steps, we actually see when you optimize for area under the curve, RMS prop oscillates a lot and Adam becomes more stable, which is not like the case in the first thing that we saw. And the thing is that it actually converges on Bayes counterexample, which is interesting, and which I would like to study, like how step sizes can actually help us with this divergence problem. Going on to why this might be happening, I plan to look into what is the conditioning of the GA matrix, because like going back to the TD update, the divergence was because A was not a positive semi-definite matrix. But what happens, like, does the RMS prop update make the GA matrix a semi-positive definite update or not? Like, I'm going to study that in the next experiment. And this is a very coarse experiment where we are applying the same update on the Bayes counterexample. The green dots show the GA vector to have all positive eigenvalues, and the red dots show GA to have at least one negative eigenvalue. And having a closer look, we often see that the points where the error is false tends to have a PSG matrix. This is not very conclusive, but it's a start. I'm not sure where to go from this, but yeah. Looking at the algorithm for general adaptive methods, there are two parts to the algorithm which can actually change how the algorithm behaves. One is the second order moment, which was introduced in which the RMS prop and Adam uses, which changes the direction of the gradient. And the second is the weighted projection operator that they use to keep the iterate inside the region of like domain of iterates. So there can be two cases of convergence because of this, and I try to investigate the projection part separately on the TD0 update. And when we do that, we actually see that TD0 might converge with the projection operator if the domain is small enough. So over here, I gave a space of 2 more units to the weight vector, and the solution actually goes down to MSPV of 0. But when I increase the space that the weight vector can move in, we find that the solution converges to somewhat of a bad point. And when I measured the angles to the solution vector also, the angles didn't change a lot. Now moving on, like I'm not sure where to go on from this direction, and I just wanted to discuss what other ways we can do this. So in the empirical sense, what I was trying to do, I was planning on sampling some random bad environments which violate the distribution mismatch, which violate the distributions property, and then observe what happens in the SGD, RMS prop, and the Adam case. And the second way is a theoretical direction, where we have two ways of going to analyze this problem. In the first case, we can look at the online convex optimization case, which I think it might not be very suitable. And in the second case is using the stochastic approximation theory. But the problem comes in because the G matrix that we consider over here depends upon the trajectory as well. So I'm not sure how to go about with that. Yeah, these are the references. Okay, that was pretty short. Yeah, and like for the empirical case, I was considering two kind of cases where I make the A to be a positive definite matrix, and in the second case, I make the second part to be like only constrain this part to be positive definite.
Are we at questions now, Dhawal?
Yeah, we can have questions.
Cool. Okay, thanks. I have a quick one. So, I mean, I'm pretty sure you're aware, but RLAI has done quite a bit of work on step size adaptation and temporal difference learning to date. Quite a few works on it. For your results, did you try like the recent tidbit method? Did you try also throwing tidbit at Baird's counterexample?
No.
No, you didn't?
So
okay.
The motivation was to study how this adaptive step size methods from the supervised learning community fit to the case of RL. Do we actually need to go and develop methods like tidbit or like say ATD to suit RL, or can we use some methods from the supervised learning community itself? That was the motivation behind this. So yeah, we didn't try tidbit just because of that reason.
Cool, thank you.
I have a sort of question or a comment. So I've also been studying these Adam sort of momentum-based methods in the non-stationary setting. And what I found that if the target function is changing very fast, momentum actually hurts tracking. So you cannot track if the target changes very fast. And that could be happening in RL setting because you're using bootstrapping and the target function changes at every time step. So maybe you will eventually find that momentum is not helpful. And that may in part explain why there has been almost no success for online RL using Adam.
So momentum in general doesn't change the convergence properties at all, because it only maintains a moving average of the gradient. What I was trying to see is having Adam, does having Adam as an update reduce the possible amount of problems that we diverge on? Like, does Adam give us a weaker condition of divergence? And that weaker condition of divergence would normally arise because of this change in direction, because of the VT matrix, the second order moment. If this is encoding some behavioral properties of the environment, like some properties of the environment or the behavior policy, then can we actually show that it is correcting the distribution mismatch in some way?
Okay.
Yeah, but I'm stuck at this point, basically.
So can I ask something? So first of all, sorry, I was quite late to the talk. I had some other meeting that came in, but I'm very curious about this whole thing. So I would appreciate if you send me your slides at the end, but my questions could be totally off or naive. So one of the things that I think is quite special about the TD setup is that we're solving this fixed point equation this way or another way. And it's different than like minimizing a loss in many ways. And in some sense, the closest to what we are trying to do is to rewrite this whole thing as a setup point optimization problem. So, you know, GTD, for example, people rewrote it as a saddle point problem. And then you could look at what people say in the saddle optimization literature. And they actually would say that, oh, you have to take like extra caution, like gradient against gradient doesn't work. It can circle. Usual step size adaptation methods don't work that well. Like you have to take caution and so on and so forth. So have you looked at the saddle point point of view?
Not yet, no.
Yeah, I think it could be the other one. I'm hoping that the saddle point viewpoint can bring some clarity to these questions. By the way,
Okay.
yeah, like I don't know, another thing, like it's maybe shameless self-promotion, but a while ago with a postdoc of mine here in Alberta, we've been working on theoretical aspects of how to choose step sizes in TD methods. And we wrote a paper about that. It appeared at the AI Stats a couple of years ago. And there are some interesting open theoretical questions. So like we figure out that if you go a little bit more general than TD, so you can generalize beyond TD, you can just say that, oh, I want to solve these linear equations with these stochastic methods when I have this noisy information about these equations that I need to solve. TD is a special case of that. Then you can't have good step size adaptation methods at all. So there is some universality is lost, but we are not sure about TD. So TD is a special case. It has extra structure. So there are some good open questions there. And I think this is a very good topic. Sorry, just.
Yeah. The main problem that we were trying to see was not exactly how Adam and RMS prop will work, but exactly if some kind of step size schedule can help us with convergence. You can always have a step size which is inverse of the importance sampling ratio, but that will eventually lead us to converge to a value function which is not the target value function.
Yeah. So maybe I can say just one, like some short thing about this paper of us with Chandru. So there we were trying to pick up the stream of work from supervised learning that was saying that there is a miraculous property for constant step size and iterate averaging on the top of constant step size if you consider linear prediction with a squared loss. Because you can have really conditioned problems, but if you apply a judiciously chosen constant step size, then no matter the conditioning of that least squares problem, you have uniform convergence rate. And that's like beautiful. Like you have adapted, right? Because you don't have to make your step size dependent on the problem instance that you're solving. So that's really nice. So we wanted to see whether this result generalizes to the TD setting. And as of today, we still don't know whether it generalizes. We know that if you would try to generalize this idea to a setting that includes TD, but it's a little bit bigger, then it can't work. So if you overgeneralize TD, then that's too big. Constant step size and iterate averaging doesn't cut it. And we don't know for TD, but also another caveat here is that if you have a Markov chain, then that's driving the whole process. And that's not what we were looking at in that paper, but we just took the simplified view that, like, first do the IID case, where maybe you have a simulator or whatnot. For some reason, you have IID data. Then constant step size averaging may have a chance, but we know that it doesn't have a chance. It's going to be biased if you have a Markov chain that's driving the whole learning process. So you definitely have to go beyond that. So it's like pretty fascinating topic, and actually it's very active in the theory literature. Like lots of people are working on this and looking at this. You can see new papers that call it an ICMR this year about this.
Yeah.
Yeah.
Can you tell me the name of the paper that you were talking about?
I send you the links in the chat, or yeah, I just post the links there. Okay.
Okay. Yeah. Thanks.
Yeah.
Hello, this is Rich. I have a few
Hi.
comments. Don't worry too much, but the argument you gave that the motivation of this work is to see how a particular methods used in a particular community have an effect. That's not really a valid motivation. If everyone did that, we would just all have people running off in particular directions for no good reason and not realizing that things were done better possibly by other people. We want to be aware of what's done by other people and from other traditions. And the answer you gave in response to Patrick's suggestion that you should include tidbit was I think your response was that, oh, you wanted to use methods that had been used in supervised learning rather than in TD learning. Well, tidbit, those are all methods that had been used in supervised learning. It's just a different community, and it has been used actually in deep neural networks and has been used in them for a long time. And yeah, it's not valid to just say, I'm not talking about those, and you can say, I haven't looked at them yet, and it would be a good addition to what you're doing, but you can't define your topic. In my opinion, that's not a valid way of defining your topic.
Yeah, I agree. But like the basic starting of the project was kind of based on that motivation. But I agree with that. Yeah, we eventually have to consider things which, like the motivation is in that sense very narrow, but the questions that it offers are more general. I think the questions that we will investigate are more general.
Good. Now, all of these methods have parameters, hyperparameters, whatever you want to call them, and I presume, I don't know, how did you? So the question is, do they converge for all values of those hyperparameters, or did you have to select? And would you find that if you didn't select them based on the problem, you would still have divergence?
Yeah, we had to select hyperparameters. There was divergence for some set of parameters, because for some set of parameters, these methods will actually become SGD. So some of these methods.
It's kind of it's not clear what kind of, if it's a meaningful result. I mean, so I want you to notice this. If you do TD lambda and you allow lambda to be a hyperparameter, then it converges. It's just on Baird's counterexample, lambda has to be high. It can't be 0. So really, the counterexamples are there to expose something that is not a problem if you're willing to maximize over hyperparameters. It's only an interesting issue. Yeah, so I'm not.
Yeah, so if adjusting lambda can actually make TD lambda converge, then the question is, how can we adjust lambda easily? Like, what is the easier way to adjust lambda? And if you can kind of shift that problem to an adaptive step size, or shift the problem from adaptive step size to adaptive lambdas, then it's okay. Like, in the end, we need convergence, no matter where we get it from. And if you can solve it from either of the way, it's fine according to me. We should have easier ways to do it. Like, it might be difficult to tune lambda when compared to tuning, let's say, the parameters of Adam or any other adaptive step size method.
Right, but you're shifting to adding a whole lot of more machinery, and you still have to optimize over parameters. Whereas with the existing machinery, if you count TD lambda as existing machinery, you just need to, the same thing. Optimizing over parameters will solve the problem. It's not clear that you have an argument that you need the additional machinery. Okay, so
what I wanted to ask was is TD lambda a learning algorithm, or is it a step size? Like, is it something which is lambda is learned at the time? Oh no, I think I'm not framing the question correctly. TD lambda is more of a method, where Adam is more of a, like, Adam for a default value just converge on this. So, and for some parameters it will diverge, but for its default parameters it does converge. if I say, yeah.
That's just a sort of an unsatisfactory answer. Probably for the default parameters of TD lambda, it would also converge. We tend to use a default value of lambda 0.9. Okay, but that's not interesting. And I wouldn't make a deal out of it. Okay?
But yeah, but does TD default value of 0.9 for TD lambda works for most of the things, or is it a thing which is used by most of the people? I'm not sure.
So, Dhawal, is that an interesting question? Or is it more interesting to choose the lambda parameter to be 0 to expose an issue and a weakness that happens in that case? We should be happy to expose the weaknesses and to gain understanding. Yeah, okay, anyway. It's good to do. I think step sizes are important, really important. And I'm glad you're working on them and exploring them. And it's sort of an extra bonus that we might be able to handle divergence issues. I think we just need to get a generally better understanding of step size methods in deep learning.
Yeah, I feel that way too.
Cool.
And I'm open to people actually collaborating on this if anybody wants to collaborate on this. Because yeah, I'm kind of stuck in this problem. Okay. Does anybody have any other questions?
Maybe just one question, like a clarification on something you mentioned earlier in your presentation. You were talking about the importance, like the effect of a projection operation when you're doing your optimization procedure. And so you'd shown two examples where you would constrain the domain of the iterates differently. Could you explain that a bit better? I didn't quite get it at the time. You talked about like units of freedom, and I didn't entirely understand what was going on.
So what I meant by that was, let's say I start from a weight vector, and by unit of freedom, I mean how much more space based on the norm of the weight vector I'm giving the weight vector to move. So let's say my weight vector has a norm of 10 when I start the learning procedure. So I give the weight vector a space to move to up to 12, norm of 12. If it gets bigger than 12, I project it back to the space of the sphere.
Sorry, wait. So when you say projecting back to the space, do you have a constrained domain from the outset, or is it somehow with respect to the initial position of the vector? Like normally there's a domain that your vectors can live in, and you always have to project back onto that domain, right? So are you changing like the diameter of that domain, or?
So for the case of Baird's counterexample, the starting weight vector is always the same. So in some sense, the domain is fixed for all the cases that I'm considering.
Sure. So if you're not changing the size of the domain, how are you changing what are you projecting onto?
So when my weight vector gets out of the domain,
yes,
I just project it back to the domain that I'm not getting the questions. Like I didn't understand the question. Sorry. Like there are two cases where in one case the domain is just a little bigger than the starting. Okay, in the first case the domain is small, and the second case the domain is much bigger than the.
Okay, so you actually are changing the size of the domain.
Yeah. For the two cases, and in the first case where the domain is small, we can see the projected Bellman error actually go to 0, and in the second case, it doesn't go to 0, but it doesn't diverge. Like it doesn't stay on the border also of the domain.
Okay, so maybe the follow up is I wasn't. Can you lead me to the takeaway from those slides there?
Takeaway is we kind of don't understand if like the projection operator then doesn't help with the convergence in these cases, and we are not exactly understanding how the iterates are behaving near the for constraint domains, I would say. Like I'm not sure of the answer myself about this.
Okay, thanks.